Hi everyone. In the previous lecture, I showed a circuit called Astable multivibrator. An Astable multivibrator is a circuit which is used as a pulse generator whose output keeps oscillating between plus and minus Vsat between two states, and the average value will be equal to the DC operating point of the circuit, which turns out to be 0. And we said that for an Astable multivibrator, the circuit should be configured in DC. At DC, it should be configured in a negative feedback mode. Okay, only then it will act like a oscillator. Otherwise, it's going to act like a latch. It'll latch onto either one of the stable states, which will be plus Vsat or minus Vsat. Now, I discussed a very interesting problem in the last lecture. I said instead of resistor, what if I replace it with a transconductor? What do you think will be the change in the circuit? Will the circuit behave any differently? So, like we did in the previous example, we'll always start with the DC operating point and see what's happening at DC. What is the DC operating point for the circuit? So I'll assume the capacitor is open, and for simplicity of analysis, I'll assume the transconductor has some finite output resistance, a very large value, but I'll assume that to be R out. So the feedback path gain is given by GM R out. This is your inverting feedback, the negative feedback path's gain, feedback factor. And the positive feedback path's feedback factor is given by beta, which is less than 1. This is much greater than 1. Okay, so because the negative feedback is much greater, feedback factor is much greater, the overall feedback is negative. Therefore, I can assume V plus will be equal to V minus. Okay, for this node voltage to have any finite value, I should assume that V plus should be equal to V minus, right? The VD has to be 0. And what is that finite value that the output will settle to? Again, you can use this, assume this to be V naught, and you will get a condition which is beta minus times V naught. So you will get beta minus times V naught should be equal to beta times V naught, and this is true only if V naught is 0. Okay, so therefore the operating point here as well, here is 0 as well. Okay, this will also come to 0. The difference here is, in the previous case it was a first order RC charging. Now you have a charging through a transconductor. So what does a transconductor do? If you apply a step input to a transconductor, if you apply a DC input to a transconductor, and then at the output if you connect it to a capacitor, if you apply a DC input here, what will it do? It will provide a constant current. The constant current, it is independent of this node voltage. It will keep on providing that constant current. Okay, so I've ignored R out in this analysis because I was just trying to use R out to show you guys to do a loop gain calculations. That's it. It makes not much of a difference. So I've ignored R out in this analysis right now. Okay, yeah. So it acts like a constant current source, and it will charge the capacitor. You will not, if you have a first order RC circuit, the charging and discharging will happen exponentially, right? That's a first order RC response. If you have a transconductor, because you are injecting constant current source into the capacitor, or you are pulling out constant current from the capacitor, the output of the capacitor will either increase linearly or decrease linearly. This is what you are supposed to expect. So it will actually behave like the same Astable multivibrator circuit as well. The only difference is that previously this node V minus was actually oscillating between plus Vsat and minus Vsat like this. It was going through an exponential discharge, exponential charging and discharging. Okay, now instead of an exponential charging and discharging, it will be a linear ramp. Okay, it will go from minus beta Vsat plus beta Vsat. When the output when the V minus becomes equal to plus beta Vsat, your output will trip. It will go to, it's an inverting Schmitt trigger, it will go to minus Vsat, and it will stay at minus Vsat till the inverting terminal reaches minus beta Vsat. When it reaches minus beta Vsat, your output will go to plus Vsat. Okay, it will trip, it will change from minus Vsat to plus Vsat, and it will stay at minus Vsat as long as your V minus goes from minus beta Vsat to plus beta Vsat. So how do you find the time periods here? Okay, so I mean, I can do an analysis. I'm doing the analysis pretty quickly here because we have already performed the analysis of a stable multivibrator. So I thought I'll do it very quickly here, because otherwise you can always start with the analysis, assume that everything is at 0 initially, and then we are slightly kicking this to minus delta V, and then what happens, this will go to plus Vsat, this will come to plus beta Vsat, and this node voltage will slowly charge to plus beta Vsat, then the output will trip. All that you can do all that analysis, but since I've already done that for first order RC circuit, I didn't want to spend much time here, so I'll leave that to you. In case you have any doubts, you can write to me, I'll explain it. So this is what the inverting terminal voltage will look like. V minus will look like this. It will go from minus beta Vsat to plus beta Vsat, and back to minus beta Vsat, and then to plus beta Vsat. It goes this way, and the output will keep tripping, changing between plus Vsat and minus Vsat. Okay, how do you find the time period here? It's very simple. It's much simpler here because there is no first order RC charging, so you don't have to deal with exponentials and logarithms. It's a pretty simple circuit. So all I need to do is, the output voltage goes linearly from minus beta the inverting voltage goes from minus beta Vsat to plus beta Vsat, and that will be your on time. Okay, that's when your output is equal to plus Vsat. Okay, you can see it here. When the inverting voltage goes from minus beta to plus beta, it's on time. Okay, so all I need to do is find the slope during the on time. The slope during the on time is simply delta y by delta x, right? So delta x is time here, which is t on. So delta v is 2 beta Vsat, right? You sub this minus this is 2 beta Vsat upon t on. This is your slope. That should be equal to the slope of your capacitor's charging. What is the slope of your capacitor's charging? During the on time, the output voltage will be at Vsat. If the output voltage is at Vsat, the current that you are injecting into the capacitor is given by Gm times Vsat. That's the constant current. So current divided by the capacitor will give you the slope, right? What's your voltage across the capacitor? Vc of t will be integral of I by c dt, right? It's a constant current, so you get this. So since it's a constant current, you will get I by c into t. If you differentiate this and Vc of dVc by dt, you get the slope, which is I upon c. So therefore the slope is given by, so you get a slope, the condition you get is, the slope you get is Gm times Vsat, that's your current, divided by the capacitor. This should be equal to 2 times beta times Vsat upon t on. Equate the two, you get t on. T on will be equal to 2c by Gm. Let's call the time constant. Gm by c, I'm calling it as time constant. So it will be 2 tau times beta. That will be your on time. Similarly, you can compute the off time. Off time is the time it takes to reach from plus beta Vsat to minus beta Vsat, right? Remember, this waveform is symmetric. When it goes from negative to positive, the waveform shape looks the same. So it exhibits some kind of an odd symmetry. So you can easily say that will also be the same. Off time also is equal to 2c by Gm times beta. You can compute the same way using the slope expressions. Compare the two slope expressions, you get a similar equation with the negative signs, but that's fine, you get this answer. So it will t off will also be equal to 2 times tau times beta, where tau equals Gm upon c. Tau equals c upon Gm. Okay, this is what I'm calling it as time constant. So the overall time is the sum of on and off times, which will be 4 tau times beta. So now if you see, right, the time period is directly proportional to the feedback factor, the resistive feedback factor. Previously it was dependent upon logarithms and all that. You had some ln of 1 plus beta by 1 minus beta. So it had some logarithmic dependence on the feedback factor. Here if you see, the feedback factor, the time period is directly proportional to the feedback factor. So I have a linear control of time period with the feedback factor. So that's the only difference here. So I just wanted to discuss this circuit here. So this circuit will also has negative feedback, and I just told you guys what will be this steady state the negative feedback DC operating point. And if you observe the output waveform, the average value, because your on and off times are same, the average value will be 0, and that will exactly match your DC operating point. So finally, to conclude, so anytime you are analyzing oscillator circuits, especially feedback based oscillator circuits, at DC they will have negative feedback. Okay, this is something to keep in mind. If they have positive feedback at DC, then the circuit will latch. Okay, it'll latch onto one of the two conditions. So I mean, I've also worked on oscillators for a very long time. So I'm working on some very interesting monographs and probably a book on on PLLs, where I'll talk about oscillators in detail, where I'll talk about some very interesting oscillator circuits, okay, which will have some all combinations of all of this and all that. So I'll go there at a much greater level. But since we are only talking about basic analysis of these circuits, keep these 2 points in mind. Anytime you are analyzing a feedback based oscillator circuit, which is what we normally encounter in most of the analog electronics courses, at DC you should have a negative feedback. Okay, if you have a positive feedback at DC, the circuit will latch. So once the circuit latches, your gains become very small and the circuit may not oscillate. Okay, thank you.